Let's make a start. Welcome back. So the next speaker is Nathanan Tantivasadakarn from Caltech, and the title is From Wave Function Collapse and Galois Solvability to the Realization of Non-Abelian Topological Order on a Quantum Device. Perfect. Right.
Thank you for the organizers for having me here. It's a great pleasure to be giving this talk. It's actually my first time in the UK, so I'm really enjoying it. So today I'm going to be talking about, as Steve already alluded to, it's some recent work on our theoretical studies into preparing non-trivial topological states, and also implementation on the quantum device. So I think, fortunately, in the morning, Mesam and Steve already did the heavy lifting of introducing this concept already to everyone, so I can go through this pretty quickly. But I just want to explain what and why, how, and why we're preparing. So what are we interested in? Oh, these are topological phases of matter, which has a long history since the fractional quantum Hall effect, and since then, theoretically, we've already seen that there are various understandings ranging from quantum spin liquids and even applications to topological quantum computation, such as the toric code or the Majorana chain. And ultimately, we want to understand this both in terms of the low energy, the lattice model to the low energy topological quantum field theory. But there are also these interesting lattice models as well, which we don't even know how to write down a good quantum field theory for, such as these fracton models. So there's a lot of interplay to study between the relation between lattice models and continuum field theory. But in particular today, I'm going to be talking about phases with non-Abelian anyons, and these are non-Abelian topological phases. And the basic idea is for an Abelian anyon, you take one, you move it around the other, you get some phase. But for a non-Abelian anyon, there's some internal degree of freedom where you apply unitary, and then you can get interesting fusion statistics. So why not realize non-Abelian phases? Well, of course, zeroth order, it's cool. But in the long term, we might hope that this would be one route to realizing universal fault-tolerant quantum computing by braiding these anyons. And of course, since the discovery of fractional quantum Hall, it's been really hard to probe and verify it in a solid-state system. But we know that recent experiments have used a different route to approaching these problems. Rather than looking or creating a material that has these properties, why don't we make them ourselves in the lab by just engineering it in the lab? So of course, there's this, what Mesam alluded to, is that there are two different ways one can approach this. I mean, so they both come under the name of engineered quantum matter, but you can either start from a Hamiltonian and try to design a Hamiltonian whose ground state has a topological order, such as this Z2 spin liquid, which was done by this experiment of Rydberg atoms in Harvard. Or you can have a quantum processor where you directly create a wave function which has the properties such as the Google experiment. They have a superconducting qubit device, and they created the toric code state directly. Now, in terms of scalability, one might ask, how does this scale up? And the problem is in creating these.
Just to be clear, the reason why we're not looking for non-Abelian phenomena in things like fractional quantum Hall materials is because we run out of materials and we don't know what to look for.
Oh, I mean, there are candidates. Just the experiments themselves to verify that we actually have created one is hard. It's hard to unambiguously verify that what we have really is that. There are, of course, different signatures that suggest, but it hasn't been clear cut in some sense. So these two experiments just came out just 2 years ago, and of course people are really excited about it. Just in terms of scalability, the problem of this approach of creating these states this way is that the time it takes roughly to prepare this scales at the system size. For example, for the Harvard experiment, what they did is they start with some trivial state, and in order to prepare the spin liquid phase, they would tune the parameters in their Hamiltonian until you gradually go into the spin liquid phase. And because they're in different phases, the gap of your Hamiltonian must close. And in order to avoid going to excited state, you want to do that adiabatically, which means that, and since the gap goes as 1 over the system size, the larger system size you have, the time to take to prepare that will scale with the system size. For the quantum device side, there's a similar bound, which is you need a linear depth circuit. So for the Google experiment, they carefully designed a very particular quantum circuit of depth, say 7 here, to prepare the toric code. But of course, if you go to a larger, suppose their chip has a more number of qubits in the future, this circuit wouldn't work, and you would have to use a different one, which would, of course, take longer to prepare. Okay, so the question we'd like to ask is, these properties of preparing states are a unitary way to prepare states. And the question is, can we use something non-unitary, such as measurement, or can we use wave function collapse, to somehow scalably prepare topological states of matter? And actually, the people in quantum information already know this answer. They would just say, oh, you have a stabilizer code, you measure the stabilizers, and they all commute, so that gives you a way to prepare efficiently the toric code. But what we want to do is see how far we can take this. Can we prepare some non-interesting state that does not admit a stabilizer code representation? And so the goal of my talk is to get to this paper where we prepared a non-Abelian topological order, and we used this trick of using a combination of unitary circuits but also measurements in order to prepare this non-Abelian topological order.
What was the red and blue lines?
The what, sorry?
The red and blue line.
The red and blue line, previous slide, or?
Yeah, this one.
Oh, this is just from their paper. They're just showing some correlation length that they show that this diverges. So this is just saying you have a phase transition here, which means that you have to go very slowly through that phase transition. Right. So the goal is to get here. So what I'm planning to do today is first explain some of the theory we explored. And what we did is, on the theory side, we showed that you can sort of rethink the way people have been thinking about measuring these stabilizers as actually gauging a symmetry. And we realized that after we are equipped with this realization, it opens up, we can now borrow the tools that condensed matter and high energy people use all the time. It's just gauging different symmetries to realize different topological phases. And in fact, we find that this gives an interesting hierarchy of topological phases, in the sense that originally you would say, if you just had unitaries without measurements, you would say every state is equally hard to prepare because you need a linear depth circuit. But now we can ask, with measurements, does some states become easier than others? How many rounds of measurements you need to prepare? Or are there even some states you cannot prepare using measurements? So that's what I hope to tell you today. And then at the last part, I'll be talking about how we use these techniques to actually prepare this non-Abelian topological phase. So first of all, before I continue, I would like to thank my collaborators. So the theory work was done with partially when I was a grad student at Harvard, and this was done with Ryan Thorngren and Ruben Brazen, who were postdocs there, and Ashwin Vishwanath, my advisor. And later on, we did this experimental collaboration with people at Quantinuum, and I'd like to also give a shout out to Mohsen Iqbal and Henrik Dreyer, who were the people who actually dealt with the quantum device and, for example, ran the machine to get the results we wanted. Okay. So in case there are any questions, let me pause. Otherwise, let me get right into the theory part. So let me just review quickly how a quantum information person would explain how you prepare the Torah code. So I would start with qubits on the vertices and the edges of a square lattice. It could be any lattice, but let's focus on the square lattice. And they would say, okay, you would put a product state on both, which is in the plus state, on both the vertices and the edges. And one nice way to explain what state you have is to denote what stabilizer this is. And by stabilizer, I just mean the eigenvalue of my state is just a +1 eigenstate of the operators I'm writing on the board. So I have a poly X here, which means that the +1 eigenstate is the plus state. And so I just have plus states everywhere. And what I want to do is try to measure the vertex term of the Torah code. So by how to measure the vertex term? Well, I want to couple these edges to some ancilla, which are the red sites, and then measure that red site. So thereby indirectly measuring the vertex term of the Torah code. So how do we do that? Well, you need some quantum gates, and it turns out that the quantum gate you would apply is this so-called control Z gate. The so-called control Z gate, basically what it does is for every S you see here, so I'm applying this to every vertex edge neighbor, and what control Z does is basically whenever you see an X, you put a Z on the side. So after I apply this gate, the state is now described by a new stabilizer state, where all these 5-body operators for each vertex and this 3-body is +1. Yes?
Sorry, you have qubits at every edge and at every vertex.
Yes, yes,
right?
yes.
And then all of them are in the plus state.
Right. Right. And right now, after I apply this circuit, this is a shallow depth circuit. Turns out this control Z is diagonal, so I can apply them all at the same time. And the state I get is just the +1 of all these edge terms, which are now 3-body, and vertex term, which are now 5-body. Okay. So this is still short-range entangled because this is a shallow depth circuit. But then comes the next step where I can now measure the vertex terms in the X basis, and that would infer what the vertex term is. So now, after I measure the vertex term, I get a classical outcome, which is +or -1. I denote that little x. But now I know that the vertex term is now either +or -1, depending on this measurement outcome. What happens to this 3-body term for each edge? Well, that doesn't commute with the x measurement I'm doing, so I don't know what this value is anymore. However, if you take the product of this 3-body term around a plaquette, you see that all the z's cancel because z squared is 1. So you're just left with the plaquette term of the Torah code, and that commutes with the measurement, so you still know that value. So this is +1 by default, and you just only have this +or -1 outcome of z's that you have to worry about. Okay. Now, this is not the desired ground state of the Torah code. You want all these to be +1. So how do you do that? Well, there's an easy way to fix it because you know you're recording all the measurement outcomes. So let's say you get everywhere is plus except these 2 positions are minus. And you know that by that you can think of that as having an E on there, and we know how to create or annihilate the E on. You just need a string of X's, and that will make the vertex stabilizers happy.
You do quantum error correcting code, yeah.
Yes, yes, yes. But you can be sloppier than that because you don't need to care about how you pair them up. So you can be sloppier than error correction, and it's a bit more efficient. Yeah. And at the end of the day, you're just going to prepare the Torah code. So even though you have measurements and measurements are random, by recording the measurement outcomes, you can still deterministically prepare the Torah code, and you don't have to post-select. Okay. So this is how a QI person would explain this to you. Now, what I want to explain is a slightly different way. I want to flip this around a bit. Previously, I said that I used the red sites as an ancilla in order to measure the vertex. I wanted to flip around in the sense that actually it's the red sites that's important. And to do that, let me explain this in a different way. So I want to say that the Torah code is secretly a Z2 gauge theory. And what we're doing by performing this measurement is actually gauging a symmetry. So usually when we think of a gauge theory, we have some sort of Gauss law which we're implementing. For example, you might have a Gauss law divergence E of 0. In this case, it's sort of a mod 2 version of that. And that is that role is played by exactly the vertex term. It's just telling you that there's no charge in the middle. But you can think of projecting into this gauge invariant subspace as simply measuring this 5-body operator as measuring what charge do you have, right? Because I'm measuring this x, and you can think of the x as being the charge, which is 0 or 1 mod 2. So if I don't get the desired measurement outcome, it means I just have a charge there. Of course, we understand that that's the E, and we just use the Wilson loop operator to pair those charges up. Now, the nice thing about thinking about this way is that I told you that the ancillas were in the plus state, but you can think of that as the fixed point of a paramagnetic state of a 2D Ising model, and by gauging that Z2 symmetry, I get exactly the toric code. But then you can see that I didn't have to be exactly at the fixed point. Suppose I'm somewhere else in the paramagnetic phase. I could sort of like have some sort of Ising interaction. If you handed me that wave function, I could have done that whole procedure that I told you, couple and then measure, and then I would still get not the toric code, but still something in the same phase as the toric code. It'll still be in the so-called deconfined phase. So by looking at this way, you now see that what we call the ancilla is actually, you should think of it as a paramagnet, and by inputting that state, we're gauging that state. So the important part is actually in the vertex term. Moreover, I don't need to actually give you a paramagnet. I could have given you some other topological order living on the red sites, right? And if it has some symmetry, then I can then gauge the symmetry of that wave function to get another state on the vertices, on the edges. So so that sort of generalizes the preparation of the toric code to potentially more interesting states. And you can do the same game in 1D. That will prepare you a GHZ state or like a cat state, and you can think of that as a fixed point of the 1D ferromagnetic state.
So you always couple the vertex and edges in the same way that you described?
Yes, yes. So because I'm always measuring that same operator, regardless of what state I started with, you're going to be measuring the Gauss law, which is why it corresponds to gauging.
So is this essentially, only when x is in the plus state, you're measuring essentially the vertex?
Yes, but if you get minus, it means you had a charge there, and you just need to pair the charge up as usual. Everything else is the same. Okay. So here's a proof why it works. You can sort of roughly think, let me just draw this in 1D for simplicity. But what the concept of gauging in condensed matter, a lot of people know this as the Kramer's Wanne duality. And you can show precisely that this procedure of starting with an arbitrary function on the red sites, initializing your blue sites in the plus state, applying this circuit, and then projecting out this red, gives exactly the Kramer's Wanne duality. And what is the Kramer's Wanne duality? In the 1D case, you can think of the transverse field Ising model where you have a transverse field term x and a Ising term zz, and those two get swapped. So in this way of thinking it, you can directly see how x turns into zz. Suppose I have an operator x here, you push it through this circuit, and I told you the rule for control z is whenever you see an x, you put a z on the side. So, and then x acts on this plus state, and it has eigenvalue +1, so you get zz. So you see that the paramagnetic term is mapped to the ferromagnetic term, and since this picture is symmetric, likewise, if you have a ferromagnetic term down here, it's going to get pushed up into a paramagnetic term. So it's actually implementing the gauging, and in higher dimensions, that also implements the gauging to prepare the toric code or other states.
Should I think of these plus states as defects, like gauge defects?
As gauge defects.
Defects
Yes,
are
you can think of them as gauge fields in some sense. And I start with a matter theory, I couple it to some gauge fields. You can think of it as something like minimal coupling. And then you sort of either perform gauge fixing or sort of integrate out the matter fields there. You can sort of think of it roughly that way, yeah. So in the end, you're ending up with a pure gauge theory where there are no more matter fields living.
You have to do the measurements? Isn't the entangler already gauging in a sense?
Yes, I do have to measure it. Otherwise, for example, in the paramagnet, right, this state is still, before I measure, it's still short range entangled, so it's not the toric code yet. it is closely related to the toric code in the sense that I will have a slide actually where you can think of it as a Higgs phase of the toric code. The cluster state is, in some sense, the Higgs phase of the toric code. Let me get back to that in a few slides.
Kramer's Vanier takes a square lattice to a square
To the
lattice.
dual lattice on the edges. Yeah. In 1D, it's
Which
just
is right.
in 2D, it's a different lattice now. You go from vertices to edges on the square lattice in 2D.
Right, but if I start with a square, I'll end up with a square. It'll be a different square, but I'll end up.
Just where the stuff is different. You move from vertices to edges.
But if I start with a random lattice, I will
Some
change
triangulation.
the lattice.
Yeah, you still go from vertices to edges, but the same graph.
And how about 3D?
Right, you'll still go from vertices to edges, but in a 3D graph of.
Won't I get plaquette degrees of freedom there?
Oh, you mean in the toric? Yes, it'll come from a closed loop in the same argument as I gave above. Yeah, but you would have the plaquette term, but the stuff is living on the edges still. So it's a plaquette term with stuff on the edge, product of all edges.
Okay, the setup that you're going to focus on. So I realize now I care what the lattice is. So tell me again what the. What the lattice is.
It works for any dimension, but I would be focusing on 2 dimensions. But it works for any dimension. You would just go from vertices to edges, and you can get a 3D toric code where you still have the plaquette term, but the plaquette term is product of edges all around the plaquette. Okay. So here are 2 quick comments in case these comments resonate to anyone. One is the relation of this so-called control Z state. It's a state before the measurement. For example, in the fixed point, you can think of it as having stabilizer ZXZ, and by just sort of flipping, you can sort of thinking of this as a state, and by just flipping the legs up, this gives you an operator, which exactly implements X being sent to ZZ. So it's sort of I'm drawing this in the language of tensor networks, but you can think of turning a state into an operator by flipping legs up, and there's a close relation between these 2 things. Okay. The second, which is related to Mason's question, is before I do the measurement, what is the state I have? And in some sense, you should think of this as being the Higgs phase of the toric code, in the sense that suppose I start with the toric code and I want to go back here, what would I do? I would measure this 3-body operator ZXZ, and you should think of that as proliferating E's with Wilson loops connecting them. And so when you start with the toric code state, you're going to get a sum of all the E's running around, and so you can think of that as a condensed theory where all the E's are sort of proliferating around. So your wave function here is a superposition of all E's at various different places.
So how far can you carry this analogy? Right? Like a cluster state is a superposition of all possible excitations of the toric code. Can you make similar statements if I pick up another anionic model?
Yes.
Create all the equal superpositions.
For a group, yes, that works. Yes.
I can get a kind of a cluster state, but could I prepare it in a simple way?
Yes. You can prepare this cluster state. The hard part to realizing non-Abelian is the measurement, which I'll get back to in a bit.
I will be able to create it in a simple way with control Z operation.
Oh, there is a control. Yes, there is a controlled operator. So there's some generalized cluster state which you can create easily. So this state is easy to create, but this step is a bit hard, and I'll explain why it's hard in a bit. Okay. So the point I wanted to make was, from this superposition, right, you're now measuring where the charges are. So out of these charges that are running all around, you're gonna, for a measurement, so you're gonna ask where are the charges, and now that freezes the charge to some configuration. So out of all this superposition, you're gonna pick out one slice of that, and out of that slice, you're gonna get just one instance of that, which now has long-range entanglement. So the sum of all the charges running around has short-range entanglement, but somehow by picking out only one slice, you're unhiggsing into the toric code phase, and that's why you can prepare long-range entanglement. So these are 2 comments I wanted to make.
Why you call it Higgs? Sorry.
Higgs in the sense that I'm proliferating the e's. So this operator is going to gain an expectation value. So you're Higgsing the e particle, and you can think of the cluster state on this last is exactly that wave function. Okay. So now let me come to the non-Abelian part. So there is a state that there is a cluster state generalization for non-Abelian groups. And now, if you are able to, so you can think of it in some sense as a Higgs version of the quantum double model. And indeed, if you perform a projection so that all the charges are in the singlet, then it is exactly the quantum double model. The problem is we don't have projection. We cannot do projection in an experiment. We can only do measurement. But what's the problem with measurement? Well, you're trying to measure the charge, and measurements and charges are irreducible representations of the group. So you're trying to measure a charge, but for a non-Abelian theory, there's a probability that you're going to measure a non-Abelian anion. Right? So if they're Abelian, you can pair them up easily. But it turns out that when you have a non-Abelian anion, the string or the ribbon operator to pair them up is still linear depth. So if you do it this way, this doesn't give you an advantage over just using the linear depth circuit to sort of carefully grow out your state in this method. So the problem is, you cannot pair up non-Abelian anions in finite time, and so the projection is fine, but the problem is you can't always get the outcome you want without post-selection. Okay, so how do we get around that? Well, if I can decompose my group, right? Basically, what I'm doing here is I'm trying to gauge its G symmetry. But if I can decompose it into simpler steps, all of which are abelian, then for each abelian step, I'm going to be pairing up charges that are all abelian, and that's easy, and that'll give me a solution to do that. So let me just show you how you would do that for S3. So S3 is some semi-direct product of Z3 and Z2. So how would we prepare this? Well, first, we would gauge the Z3.
Why don't you throw them out of your system, open the boundary and move them out?
Oh, you mean condense them on the boundary? I think
That's still linear
it's
depth.
still linear depth, yeah. Because it might be like right in the center.
Then it's independent of what non-Abelian anions you use.
Right, but it'll still take a linear depth. Okay, so for example, how would we prepare S3 topological order? Well, the simplest way is let's first gauge a Z3 symmetry that prepares me the Z3 version of the toric code. And then, naively, if I just gauge the Z2 right afterwards, I'm not going to get S3 because the Z2 here has to act on a non-trivial way in the Z3. I'm just going to get Z6. So I would need to apply some unitary such that the qubit part is acting correctly on the Q-trit part, which is already in the Z3 toric code. And roughly that you can think of that as some controlled operator where controlled on the Q-trit, where the Q-trit part is just swapping states 1 and 2, for example. That's how this action is working. So once you apply this, and then you perform the usual gauging, you will get S3 topological order. And now in each step, you're measuring Z3 anions, and then you're just going to do a feed forward to pair this up. So that's fine. And then you will gauge the Z2 part, and this charge you're pairing up turns out to be the sign rep of S3. And that's also abelian, so that's fine. So that's how you would prepare S3. Now, why can't I just do 2 measurements at once? The problem, why can't I delay this measurement till later? The problem is, if I didn't pair this up, what happens is, since the symmetry action permutes E and E square, if I perform this gauging, this E and E square will transform now as a doublet. So you're going to get a 2-dimensional representation of S3. And now that charge cannot be, now you need a linear depth to fix it. So you need to fix this before you do the next step. And that's why you need 2 rounds of measurement. Yes?
What does KW stand?
The Kramer's one, yeah. Basically, I just mean some operator that will gauge Z3, some operator will gauge Z2. So you can write this formula down exactly that this formula is exact, but I don't know how to do this with measurement, but I can split it into 2 steps, each of which can be done with measurement. So more generally, for any, suppose you have an Abelian extension, an Abelian group, you can also break it down similarly. And the unitary you use to entangle, so for example here, you would gauge the normal subgroup first. Before you gauge the quotient, you would apply some unitary, and the unitary just basically depends on the type of group extension you have. So for example, if you have a split extension, you would want your symmetry to permute the anyons correctly. If you have a central extension, you want the symmetry to fractionalize on the anion correctly. So, but based on that knowledge, that tells you what this unitary is supposed to be, so that you get the right group extension. Okay, so now what non-Abelian groups can we gauge efficiently? Well, the answer is known in math. Basically, any solvable group would do. And just to recap, what is a solvable group? You start with a group G, and you compute the commutator subgroup and the commutator subgroup of that. If you go all the way and reach the trivial group, that group is solvable. So this sequence allows us to build it back up, right? So I just need to start with the trivial theory. I gauge N1, and then I need to do some unitary, which depends on the information of this group extension. Then I gauge the quotient of this, and I keep building up until I reach my desired group. So you can show that, so we have a circuit which does this explicitly for the quantum double, this decomposition exactly for the quantum double. Okay, so by now you might be thinking, oh, measurement is so powerful, it allows us to prepare all of these interesting states, but is there something even measurement cannot prepare efficiently? And the answer comes from Galois. Galois tells us that basketball is easy, volleyball is easy, but playing soccer is hard. And by that, it just means that the symmetry groups, if you have a quantum double that is a symmetry group of the basketball, that's easy to prepare. But Galois tells us if you want to prepare the quantum double with the symmetry group of the soccer ball, that's hard. So you might have also heard of this fun fact that for the quintic polynomial, there's no solution in terms of radicals. And that's the exact same reason as why quantum double, we think the quantum double of the symmetry of the soccer ball is hard to prepare. So for example, this A5 is the smallest group in which it's not solvable. And so we think that, we have a conjecture for which we have some physics argument to believe why it's true, but it's not on sort of firm mathematical ground, so it would be nice to prove it rigorously that for any quantum double corresponding to, for example, the symmetric group, or for n greater than 5 or any other solvable group, we cannot prepare it explicitly using finite depth circuits and measurements. So let me now pivot to an even more strict problem, which is measurement as a scarce resource. So we do know that, so let's say I want to say that, let's ask, suppose I want to prepare a state, how many rounds of measurement do I need to need? And why do we care about this problem? Well, Steve already mentioned this performing the measurement in a quantum device is actually pretty costly. And so if you can minimize the number of measurements you need to use, then that would sort of be easier to prepare. And moreover, you can ask, like, instead of all states are equally hard to prepare, you can ask whether this gives you a hierarchy or a sort of complexity class of how different topological states grade depending on how many measurement rounds are required. Okay. So, but let's suppose I want to ask an extreme case. What if I only give you one round of measurement, right? What if you only get one shot? Can you prepare anything that's beyond a stabilizer state, which will give you Abelian topological order? Right. So we know that stabilizer states are easy to prepare. You just measure all the stabilizers and fix the outcomes. But can we get something that's beyond Abelian topological order? Right. So let me explain how to do that for D4. So it doesn't work for S3, but it turns out to work for D4. So naively, what you would do for D4, based on what I've told you, is that you decompose it into a normal subgroup, which is Z2 times Z2. And that's, you can think of that as the horizontal and vertical reflection. And then a Z2 which swaps the two. You can think of it as a diagonal reflection. Okay, so how would that work? Well, first I want to gauge the normal subgroup, which is Z2 times Z2. So I would prepare 2 copies of the toric code. I would measure the anyons E1 on the first layer and E2 in the second layer. I would clean that up, and then I would apply some unitary and more or less measure to gauge the swap symmetry. After I gauge the swap symmetry, that gives me D4. Now, what happens if, again, similarly, if I didn't clean up this step before, E1 and E2, when they swap, they perform a doublet, right? And in the end, that would give you a non-Abelian anion, which you cannot fix. So you need to do 2 rounds. So what's the trick to do it in 1 round? So there's a different way to prepare the 2 copies of toric code. Instead of measuring the vertex of the first copy and the vertex of the second copy, what if you measure this combination, E1, E2 as a bound state, and M1, M2 as a bound state? That means that you can think of that as like measuring the product of the vertex term of 2 copies and the plaquette term of 2 copies. Why does that help you? Well, now this anion transforms under the singlet, under the swap symmetry, is invariant. So if I also measure the swap anion, I gauge the swap symmetry, this will still be an Abelian anion. So this tells you that I can actually, if I measured it this way, then I can actually measure all 3 Abelian charges at the same time, and that will actually prepare me D4 topological order. So a fun comment is just this way of thinking of preparing D4 topological order by gauging this sort of different set is exactly Morita equivalence. You can rethink D4 as secretly being some Z2 cube with some with an SPT. So there's some 3 cocycle, but these 3 charges are the generators of my Z2 cube. Okay. So more generally, what can I prepare in 1 shot? The answer just turns out to be any anion theory that admits a Lagrangian subgroup. And I put group here in contrast to more general algebra is just because I want them to all be Abelian bosons, such that they have mutual braiding amongst all themselves, but they confine all the other anions. So if you can condense all the anions in A and they're all abelian, that would give you a short-range entangled phase, which is an SPT protected by exactly this group A. So this is easy to prepare, and then you can gauge this asymmetry, and that will just mean you measure all these anions, which are abelian, and then you can pair them up. And for the quantum double of groups, G just turns out to have this property. It has to be so-called nilpotency class 2, meaning it's an abelian, a central extension of 2 abelian groups. Okay. So what do we get? What we find is we have this hierarchy of topological phases. I explained how toric code can be implemented in 1 round of measurement, D4 in 1 round of measurement. So the dotted line just refers to how many rounds I need to prepare it. S3, on the other hand, needs 2 rounds of measurements because it turns out it doesn't have a Lagrangian subgroup. And you can play the same game for other groups A4 and S4. You can still prepare them, but once you get to A5 and S5, we think you cannot prepare them. And we think there is an interesting relation to this comment that came up early this morning about universality for topological quantum computation. So some phases, such as Fibonacci, is universal by braiding alone, and it seems that, so you can also generalize solvability to more general categories, and Fibonacci is also in that sense non-solvable. But we think, so it's curious to notice that these things that are universal, we cannot prepare efficiently. So is there a deeper connection between the 2? And also, there are some that are solvable, but not nilpotent, such as S3, and they're universal by braiding and measurement. But these seems to be the one exactly that you need 2 rounds to measure. So is there any deeper relation to explain why this is the case? That if something is universal, do you need more than 1 round of measurement to prepare it? So I think that's an interesting question to explore.
What about the chiralizing anions?
Yes. So since you brought it up, you can ask, can you prepare chiral states? And I put a different sort of box around it, because what we believe is that if you have sort of strictly local gates, like in a quantum processor, that might be hard. But if you're allowed sort of more general Hamiltonian evolution, and that Hamiltonian has tails, then you can prepare chiral Ising. And the idea is, for example, how do you prepare? We know how to prepare a double Ising by gauging. So you take a Z2 toric code and you gauge the EM duality, and you get double Ising. But now you need some sort of Hamiltonian evolution, we think, to separate the Ising and anti-chiral Ising from each other. Then once you have that, basically you can measure away the bottom layer, just measure it in some state. You get a product state, so you kill that, and that gives you a way to pair chiral Ising. So we think you cannot do it with strictly local circuits, because if you were able to do so by this method, that would give you a Pep's realization of a chiral theory, which people believe not to be possible.
So the chiral Ising is also nilpotent?
It's also nilpotent, yes.
Yeah. And so so you think nilpotent, say again what you think is the difference between nilpotent and solvable?
You mean the definition or the?
No, I know that in terms of what the outcomes would be, like what you can prepare. And
people know that certain groups that are non-nilpotent, S3, are universal by braiding measurement. But we don't know an example of a nilpotent that is universal.
So there's something interesting about nilpotent groups.
Somehow, potentially.
Yeah. So the double, so if you look at the Digraph-Witten theory, and look at the link invariant that you get out of it, for nilpotent groups, it's constant on knots. So the invariant that you get, so if you just take a knot and compute the invariant that you get just for a knot with any nilpotent group, it's constant. It doesn't matter at all. So that's something that does separate maybe between nilpotent and just solvable. Just a thought.
Okay, I should definitely ask you more about it.
Well, I just had a comment and a question. The comment is for the chiral Ising. Of course, if we have two layers and we have defects and we add measurements,
right,
it can be.
I'm also confused about that point, and because you have to define nilpotence for the defects, and I think in that example, it's still a nilpotent, so I'm still a bit confused about what happens when you add defects, or how should you think about it. Of course, this is just a conjecture, but I'm glad to be proven wrong.
The question was for if we thought of the double of Ising, the 11-1 model, are you thinking, if we think about it as gauging the EM duality of toric code, does that count in your language as just one round of measurement?
No, because you have to prepare a toric code first, and then, yes. And it corresponds to the fact that you have to condense psi bar first, and you cannot kill it by just condensing psi bar alone. But if you had fermions, then maybe you could cheat a bit more. But then you need physical fermions in here. Then you can gauge fermions.
We need that for the chiral Ising as well. Can we chiral Ising in one shot?
Right. Then you can prepare P plus IP and then try to gauge that.
What's the state of play with preparing fractone orders?
Yes. So most of the examples of fracton orders people have in the literature are all abelian. So in the same sense, you can also prepare them if we also talked about that. Okay. So let me now move on to the experiment, and just before I get to that, let me give a bit more intuition on what is the state we want to try to prepare. Now,
Sorry. So D4 is pretty unique in a sense.
In the sense that
Of what you can do, we can do, yes.
in terms of preparation or computation.
That's right.
So there are other groups that also satisfies this property. Quaternion is one.
That's right. Yeah.
In general, any group that can
But
be.
it will be harder. Things will get only worse.
As long as an abelian a central extension of two abelian groups, that is also one shot.
Similar. Okay.
Okay, so what is the state I want to prepare? Just to recap, going back to the toric code, what is the toric code wave function? It's just a superposition of all closed loops. And and once I gauge, this loop is allowed to end, and that gives me my M particle, right? That's how sort of like I start with domain walls. I make these domain walls actual sort of variables, and they can end, and that's an abelian anion. So what is the state we're trying to get, which has a non-abelian anion? So now I have 3 copies of Z2, and basically I'm going to call them red, green, and blue, and they have their own fluctuations as usual. The only change I'm going to do is a minus sign. So whenever red, green, and blue cross, you apply a minus sign. That's the only change I'm doing. And you can think of that as coming from this 3 cocycle. When sort of 3 things cross, I'm just going to add this minus sign. But this simple minus sign is going to have a drastic effect, and it gives you non-abelian anions. So let me just explain quickly that you can introduce this minus sign very simply on a lattice by a so-called control-Z gate. It's just measuring whenever all the spins are down, you get a minus sign. But there's a very nice interpretation of this state. So I'm going to start with the lattice where I have red, green, and blue. I start with the triangular lattice, and I color the vertices red, green, and blue. And I'm going to apply this so-called control-Z on this wave function. A nice way to think about it is, suppose I initialize all the states in the plus direction. And now let me write just the red guys as a superposition of up and down. So I have a superposition of up and down for all the red sites, and you get you can denote where up turns into down, and you can call that your domain wall. And notice that it lives exactly where the green-blue spins are living. Now, what is this control-Z doing? It's applying the so-called control-Z whenever the red is pointing down. That's the controlled operator. If red is up, you do nothing. If red is down, you apply control-Z. So you notice that whenever, if red are both up, then I do nothing. If they're both down, I apply twice, which is also nothing. It's only when there's a domain wall that I apply a control-Z. So you can think of this wave function as literally putting this 1D cluster state that I told you earlier on a red domain wall. What's special about this 1D cluster state is that so I have a green-blue cluster state living on the domain wall, but if this cluster state is allowed to end, it turns out that it's a symmetry-protected topological phase. If I allowed it to end with a boundary, then it's going to have a 2-fold degeneracy on each side, which cannot be lifted unless I break the symmetry. But once I gauge this symmetry, the endpoint here is 2-fold degenerate, but now the symmetry is gauged. It's not physical anymore. There's no local perturbation I can use to lift this degeneracy. And so this M now effectively becomes a non-Abelian anion precisely because of this degeneracy. So you can think of the non-Abelian anion as sort of like an endpoint of a 1D cluster state. And this sort of argument you can use to think of the 4 topological order as in terms of this twisted Z2 cube Dirac-Witten theory. Another nice thing you can think about is instead of thinking of a 1D cluster state decorated on red domain walls, another nice property is that suppose I have this red cluster state, a red domain wall with a green-blue cluster state, and now I insert a green domain wall, you'll see that there's a single charge here, and that comes from the fact that the 1D cluster state, once you sort of pierce or change the boundary condition for one of the spins, it'll introduce a charge for the other spin. And basically what I'm saying here in terms of math is basically the Knuth formula. So you have sort of a 3 cocycle involving 3 Z2s, and you can decompose that into from H3 of 3 Z2s into H1 of 3 different Z2s. And by going down 1 dimension, I get the cluster state. Going down 1 more dimension, I get a charge.
I have a question, and maybe since I don't know much about what you're saying, you may be contained in what you just said, but I'm not sure. So you described the difficulty of creating these things in terms of the groups, but you're actually constructing this in terms of a Morito equivalent. And how do I know that there's not a shortcut if I try to make them Morito equivalent? It can be easier or harder that way.
Yeah, I also think that's an open question. Like, given an anion theory, what's the shortest route down? And by going down, you need to choose to condense some abelian anions, and there might be more than one choice. I don't know if that length is always path dependent or not. So that's not clear to me either. Okay. So with this in mind, now I can explain what we did on this H2 quantum processor. Let me just flash some specs of. So what they have is a trap ion quantum processor where they have 32 qubits, and what they have is some sort of racetrack architecture where they can shuttle these ions around, and whenever you can put them into these interaction zones and shine lasers on them basically to implement these 2 qubit gates. And one very nice thing about them is that they have extremely high single qubit and 2 qubit fidelity. So this is the order of 10 minus 5. 2 qubit is 10 to minus 3. Okay. So what is the circuit we use to prepare the state? We start with the product state again on this. So we start with a triangular lattice, as I said. We can apply this control Z to prepare the SPT. Here it turns out that you can apply it using some ZZZ rotation, which is sort of which decomposes very nicely in their platform. And it also prepares the SPT. Now, once you have the SPT, what you're going to do is to gauge the Z2 cube symmetry. And by that, what you do is you couple extra ancillas for each subcolor. So for example, for the green superlattice, I have these vertices. I'm going to couple them to edges that connect the green vertices. So I'll apply some control Z gate, and then the projection is performed by measuring this feed forward. Okay. Now, once you projected out all the vertices, what you're going to be left with is some sort of overlay of 3 different colored lattices, and it just looks like this Kagome lattice I'm showing you here. So once you get that, you can say, okay, what is the wave function we prepared? So you can, if you work out what happens, you can describe the state we prepare as being quote-unquote stabilized by these operators. I say stabilized in quotes because these terms actually don't commute, but you can still describe the state we prepared as the +1 eigenstate of all, mutual +1 eigenstate of all these operators. So you have some star term which have 6 x's, and there are a bunch of control z's here. If you ignore the control z's for a while, you'll see that in this superlattice, this sort of just looks like the vertex term of a green toric code. And here, this is also basically like the plaquette term of a green toric code. But the fact that you have this control z is doing sort of this twisting or decoupling to take care of that minus sign I mentioned earlier. So what are the excitations? The charges are still abelian, but now the fluxes, as I said, you can think of it as being decorated by this 1D cluster state. The endpoints have a degeneracy, and they're now non-abelian. So the charges and fluxes still braid with the -1, but now the non-abelians are a bit more subtle. They're non-abelian, and instead of just using a product X as I would usually, I now had to apply these extra control Z's. And you can sort of see that because this star operator is like a closed loop of an M, and so you sort of have to also apply these control Z's in order to make sure that they commute with this bucket. Okay. So after we did this, we can measure these operators, right, and see how close we got to the ideal. So once we after preparing the state, we measured these operators, and we find that they're all all of them in the 90% range. You can also measure for the quote-unquote logicals, which is a product of z's around the torus, and with these logicals, that completely specifies the state we prepare. And in the ideal case, they should all be +1, and here we all find them in plus 0.9-ish. Okay, and using that, this gives us a bound of the fidelity per of the state per site to be 98.4%. Okay, so we prepared an interesting state. The next question is, what else can we use to confirm that we prepared an interesting state? So there are 4 things we did. The first is, unlike abelian anion theory, such as the toric code, the interesting thing is that you don't have conservation of charge anymore. In fact, you can have a ground state which has a single charge on the torus. moreover, you can also prepare these different 22 states, which satisfy the star and the plaquette term being simultaneously 1. And 22 is interesting because for an abelian topological order, if it admits a gap boundary, this number must always be a square. So the fact that you find 22 is some signature of it. The third is that the braiding follows the fusion outcome. And then lastly, I'll get to this Borromean braiding in a bit. So I just want to give you some intuition on how these, how to see all this basically from the cluster state.
Matt?
Yes.
Why is the 22 a confirmation? How do you know you just didn't miss some of them?
Yes. So the things you miss are exactly single anyons on the torus. So let me try to explain this a bit. So you might say, what I'm able to toggle. What are the logical states? There are z eigenvalues, right? And you can have them to be plus or minus 1, like the Torah code. So you would say, why are they only 22 states? Why are they not 64? Right. And the resolution is because how do you change a z from plus 1 to minus 1? You have to tunnel an m around it. But if you tunnel, say, a red anion this way and a green anion this way, that creates a single charge, which is a blue charge. And so all the other, like 64 minus 22 states, are exactly those that have an odd number of charges on the torus. So you can see that directly from sort of this picture. So here I have the red eigenvalue being minus 1, the green horizontal one being minus 1, and then we see a single charge violated here.
What about measuring the loop value?
The loop value.
Yeah. Like just the dimension of the simple object. Is that something you can do?
Sorry, what do you mean by the
quantum dimension of an object? Like, so this is what we would call the loop value.
Oh, I see what you mean.
'Cause if you can show it's not 1, then you've also confirmed non-Abelian.
That's true. That's true. I'm not sure how easy it is to do that, but these other measures are sort of also indicative. That's a good question. I'm not sure off the top of my head now. So what are the 22 ground states? There are, well, by ground states, there's no Hamiltonian here. I just mean the 22 states where the vertex at the star and plaquettes are simultaneously 1. There are 22 states which satisfy that. How do we get the 22? Well, the demand I need is that I don't want to create these sort of single anions which come from the intersection of these red or green fluxes when they intersect. So they either must not intersect or they must intersect twice. And so if you do this counting, you see that I can do the vertical ones for which there are 7, except the trivia one, the horizontal, that's another 7. And you can put them, you can both have vertical and horizontal present together, that's another 7. So that's 22. After we've done this, so we apply the string operator to do all this, and then measure the star and plaquettes again. And we find that, okay, they're still in a pretty good shape. So it still satisfies the +1 condition. Okay. Next is toggling the fusion outcome. We create 2 green fluxes and 2 blue fluxes, braid one around the other. And why do we get the charge coming out? Well, it's because the blue has a red-green cluster state, for which if I thread a green domain wall, which is exactly this green flux through, you're going to get a red charge, which means when you fuse them back, the red charge must appear. Similarly here, the green has a red-blue cluster state, and I'm threading a blue flux. So in the experiment, what do? Well, you create a green and a blue. You fuse the green back first. You get 1 charge. And then when you fuse the blue back, you find there's another charge left. And notice that while I'm opening this up, the expectation value of the star, which measures the charge, is 0, which means it's not well-defined, right? Or it's sort of, the charge is not well-defined near the endpoint. It's only when I fuse it back together that then I can read off the value. Okay. So the last thing is intrinsically non-Abelian braiding. And in some sense, these anions know all about knots and links, right? So in particular, abelian anions are only sensitive to pairwise braiding, meaning that if you link M and E, you get a -1. If they're not linked, you'll get a +1. But there are links such as this one, called the Borromean ring, for which pairwise, the 2 of them are not linked. Right? And it's called Borromean ring because of this factoid here, which you can read about Italian families and betrayal. Or but in any case, the red and blue are not pairwise linked, but somehow you cannot disentangle You cannot pull it out of each other. So it means that if any of these were abelian, you would have gotten a +1. So the fact that you measure -1 means that all the 3 that participated must have been non-abelian. Okay. So how do you see this is the case? Well, let me refer back to the how this is sort of like a quote-unquote proof. I can take this green-blue picture, which I had previously. I braided them. It spit me out a red charge. This red charge can be detected by the red flux. Then I sort of mirror this. I undo the process above. But we know that once I fuse the green fluxes back together, there is secretly a red charge in there. So even if I didn't fuse them back, they should still be there. It should still be detectable by this red link. So I don't need to fuse them back together here. Same thing for the blue here. I can just push it through, not fuse them back together. And now you can stare and convince yourself that topologically this is the Borromean ring. So how do you implement it? Well, we sort of did that experiment where you don't fuse the green and blue back together. You measure the red charge here and you undo this, and that's the Borromean ring. And then you find that up to some constant prefactor in front, the amplitude, the phase you get also here is very close to the expected value of I as pi. I wanted to also emphasize that in order to do this experiment, the all-to-all interaction of this platform really helped in order to do this experiment. Because how do you want to do it? Well, you have to couple this to an ancilla. I think Steve explained something very similar this morning, where you have an ancilla in the plus state, and if the spin is up, you do nothing, and if the spin is down, you control this whole operation. So you can imagine how deep of the circuit this must have been because it involves x and control z, and now you have to control this whole thing. But the fact that we get a pretty good value is quite remarkable. Okay. So
you get also the amplitude high, or is it reduced?
I think it was around 0.8, if I remember correctly. But what we did was you could also compare it to the case where we did the linking differently, and you would also get a 0.8 without the phase factor. So you can sort of compare the phase part. Okay. So here are some other fun facts that I wasn't able to talk about today, but are nevertheless interesting. We have an argument that I mentioned that by measuring this cluster state, we are able to prepare the Tora code phase. We also argued that in general, as long as you are in some symmetry protected topological phase, measuring the charges of that state should in general give you long range entanglement. And sort of the idea is related to some anomaly, whereas, for example, in the Tora code, you can think of there's an anomaly between the Wilson loop of the E and the Wilson loop of the M. In some sense, by going from the domain walls to the loops of the M, you create a state which has some symmetry that's anomalous. And if you have an anomalous symmetry, you cannot have a short-range entangled state. So that would be interesting to see if we can use this to prepare other interesting states in higher dimensions by measuring other types of SPT phases. The second is related to gauging a fermionic symmetry. So there are generalizations of Jordan-Wigner to higher dimensions that uses gauge theory to sort of avoid this sort of snake. There's a similar way to gauge this using by coupling fermions to bosons and measuring the fermion parity. So you can use this to create fermionic gauge theories if you have access to physical fermions. This point about chiral phases I already probably mentioned. Suppose you want to prepare chiral Ising or maybe the Laughlin state. You can use measurements as long as you have more general local unitaries that potentially have tails. And then the last point is related to stability of the preparation. So for example, you can look at the difference between preparing a 1D ferromagnet versus a 2D ferromagnet, the GHZ state, and study its stability. So for example, if my preparation or the unitary was imperfect, or I measured a bit off the X basis, does that affect anything? So it turns out that the 1D state is unstable to that, but the 2D is much more stable, and that's, in some sense, you can think of it as related to the fact that the 2D ferromagnet is stable to finite temperature, whereas the 1D state is not. So that also applies to the 3D toric code, where there are, in fact, two ways to measure it. You can measure the vertex term, or you can measure the plaquette term. And it turns out that measuring the plaquette term, where you measure where the loops are, is much more stable than measuring where the charges are. And you can even sort of take this sort of coherent noise as like your imperfect preparation and sort of say, what if we crank it up? Can we go through a phase transition in 2D where we go through some, if we mess up, we won't prepare any interesting state. In the limit, we have a stable phase. So is there a phase transition? And we recently implemented, tuned through this phase transition explicitly in IBM's quantum device, where you can actually map this tuning we did exactly to the random bond Ising model, and it's sort of related to, for example, it tracks exactly this Nishimori line. Okay. So let me conclude with some outlooks for interesting work in the future. So of course, I mentioned that D4 is not universal, but it would be interesting to prepare other states which would be interesting for universal quantum computation. And of course, you need to perform active error correction in these 2D phases in order to stabilize it. So work needs to be done in order to figure out how to do that explicitly for certain models. That hasn't been explored too much. A second one would be to prove rigorously that these non-solvable groups cannot be, I should have said, prepared with circuits and measurements. I only presented that what gauging can do, but so I said that measurement can perform this gauging, but maybe there's some other way that you can cheat such that you can prepare these non-solvable groups. So we have a pretty good physics argument for why that shouldn't be the case, but it's still not clear for us how to make that rigorous. And you could ask, what if you allow some other non-unitary process, such as more general quantum channels? Does this sort of hierarchy still holds, or is there any change to it? The third is this classification of measurement equivalent phases. So I said that toric code is now the same equivalence class as trivial under measurements. We know that anion theories are classified, we believe, are these unitary modular tensor categories. What captures this sort of structure when you impose this extra equivalence? What do you call them now in mathematics? And also, an interesting thing is that by thinking of gauging from measurements, there are also these recent other contexts where Floquet codes have appeared as a new way of doing error correction. Margarita will be giving a talk about Floquet codes. And is there a way to understand how to think of these measurement in Floquet codes as some sort of gauging? Because indeed, condensation, you can think of it as gauging some higher form symmetry. So if there are any interesting connections to that. So with that, I think that's all I have. Thank you.